Hi everyone, so we'll be starting on the webinar right now. So thank you for joining today's technical topic webinar. You guys might be seeing an unfamiliar face today. Our usual moderator Riley is off unwell, so I will be moderating today's session in place of him. I am the marketing officer here at EIT, so welcome everyone. Our webinar today will cover the current trends on concrete as a construction material to capture CO2. Dr. Anna Evangelista, who is our experienced civil engineering lecturer and coordinator here at EIC, will be presenting on this session today. Before we kick off today's webinar, I would just like to address some housekeeping matters and some common FAQs that we get all the time, which would be good to bear in mind as you participate in this session. And could you click to the next slide? Next. Next, please, Anna. So housekeeping matters. So we highly encourage participation during the session, but as a result of that, there might be a huge volume of messages going up in the chat box. So we really recommend turning off your notifications beforehand. To do this, it's really simple. Just click on that little settings icon at the bottom right of your screen. Toggle to notification settings and untick all the options so that you're not receiving both notifications as well as audio notifications that come through. Next slide, Anna. Some frequently asked questions that we get all the time. So presentation slides. For everyone who has registered for this webinar today, you'll receive an email with a copy of the full presentation slides for today's session. Please allow within 1 to 2 business days from when you complete the survey to receive this in your inbox. If you do not see it in your inbox after that 1 to 2 day window, then please check your junk folders because it might be sitting in there. For your certificate of attendance, if you would like one, please request it at the very end of this session by filling up the short survey. There will be a QR code and a QR link. The QR link will be for those of you who might have problems scanning the QR code. All of this information will be provided at the very end of the session. As mentioned, when our presenter, Dr. Anna, has finished, you need to scan the code or access the link, fill out the survey, put in your details, and we will then send the cert of attendance to you, preferably within the next 4 business days. Please do note that if it has passed 4 business days, the QR code and QR link will expire and we will not be able to issue you the certificate. I saw some of the questions asking about the certificate of attendance, so you have probably requested it after the time window, so make sure you are requesting it within that 4 business days time window. Regarding questions, if you have any questions, we are definitely happy for you to leave them in the chat box as the session runs. Any interaction is definitely appreciated from us, but we will aim to get to most of them at the end of the session. Next slide, Anna. So just a bit about EIT. If you are joining our webinars for the first time today, welcome. We are one of the only institutes in the world specializing in engineering. We currently deliver a range of courses across civil, mechanical, electrical, and industrial automation engineering, ranging from industry-focused short courses all the way through to a Doctor of Engineering. So all of our courses are offered online and also on campus for certain courses, which means students can study from wherever they are in the world, but also experience studying engineering in Australia if they want to. And currently we have students from over 140 countries studying with us. And that's all from me, and now I'll pass it over to Dr. Anna to deliver the rest of this session. Thank you, everyone.
And yeah, the main idea today is to discuss the sustainability in engineering, pretty much covering the concrete. Concrete is a material, in terms of the applications, there are so many diverse applications of concrete around the globe. But we need to consider one of the main problems about concrete is about the carbon emissions. And that's why we'll start this webinar discussing the concrete composition and its carbon emissions, and then we can uncover the other side, the carbonation of concrete and how concrete can contribute to mitigate carbon dioxide emissions as well. And at the end, I will discuss some current improvements. And you have our Q&A session just to discuss with you if you have any doubts, any questions. So to start this webinar, this is one of the questions engineers we are asked to reflect and to think about our role as engineers, how we can contribute to live in a better planet, and sustainability engineering, why it's important. All of us, I'm pretty sure each of you are totally aware that one of the main difficulties we are facing nowadays is regarding the natural resource. No, we need to figure out some alternatives, we need to be creative and innovative to find solutions to avoid the depletion of natural materials, right? It's not only about, I think, I don't know if you agree, but it's not only about the future generations, but what's happening with us at the moment. And yeah, we more and more, we are asked to work in a multidisciplinary team, right? Engineers, we are leaders in planning, not only engineers, we have engineers, architects, construction professionals. We are in charge of planning, design, building, so that's more than enough to think that we need to consider how we can ensure the sustainability, a sustainable future in our professional life, right? So we are the bridge between the science and society. So that's why today the main idea to discuss the question of alternatives the researchers around the globe are considering to mitigate carbon dioxide emissions and how we can do this. This is one of the main points to discuss regarding sustainability. As you know, more and more we are asked to reflect to have 17 sustainable development goals. But I want to highlight just these two sustainable development goals. If you think about engineering, definitely you need to think about infrastructure projects. We also are asked to contribute to live in a sustainable city, inclusive city, safe and resilient. So I really like these two United Nations Sustainable Goals because I think this is totally related with our profession, because we need to consider the health and economy. We have the health environment, right? It's not only, we need to, that's why sustainability is one of my passions, because we need to combine the social aspects, economic aspects, and the sustainability aspects. So the environmental impact aspects as well. So this is one of the motivations to discuss this topic today. Okay. So moving on, this is one of the points that we can consider regarding the topic we are covering today. How we can reduce environmental impacts. We think about at least architecture, engineering, and construction sector. We have some alternatives here, right? We can reflect. We can use construction materials with lower embodied energy. We can also consider the reduction in terms of the transport of materials, depends on the type of fuel. We can, if you just plan the transportation, the supply chain, we can also reduce some carbon emissions as well. And the other point that we can contribute when we recycle materials is to avoid waste going to landfill. This is one of the main problems we have in our large and big cities, right? Depends on the population growth. We have some limitations in terms of landfill. And modern construction, the current trend in different countries, it's about designing and construction for ease of reuse. What we want to target here. Also recycling at the end of life. So the main idea is to assemble and disassemble. So what we have here is some opportunities to consider modular construction, for example, right? To avoid the demolition of some buildings. Let's say we have a school and you don't want to use this school anymore. What can be done? Right? It depends if you are working with prefabrication, if you are working with modular constructions, all these alternatives can be easily implemented. So regarding materials, today we'll be covering concrete, right? One of the main issues we have in terms of construction materials around the globe, the total volume of cement production is around 4.5 billion tons. It was in 2021. So in 1995, the production was about 1.4 billion tons. So the cement production definitely is an indication of economic growth as well, and the growth of construction industry. And that's why we are, I'm 100% sure that you are very familiar with the concrete composition, but now I just want to ask, I will make questions into the chat box. As you know, concrete, this is the traditional concrete, conventional concrete, when you combine Portland cement, natural sand, natural coat aggregate, water, and we have some special types of concrete when you can incorporate fibers, can be metallic fibers, can be organic fibers, depends on the country, and some admixtures and additives. So here, this is the question. Why I'm highlighting the Portland cement? Why Portland cement is totally related to the topic we are covering today, carbon dioxide. And my first question for you all, I wanted to quick answer via chat box. Which country has the largest cement production? Can you please type into the chat box? Let's guess. Which country has the largest cement production? USA, Pakistan, China, India, USA, Pakistan, China. Some of you are in the right track, some not. That's why we'll be discussing this today. Yeah, China. Yeah, let's go to the next slide. Thank you all for sharing. That's great. So I'm highlighting cement Portland here because, as mentioned before, cement process is the main reason why the concrete industry makes up 8% of overall global emissions. So the process of cement production, this is the main problem. This is the true problem when you think about carbon footprint. And yeah, we need to, first of all, we need to understand the process quickly, right? I don't want to bother you that much into this sense, but we need to consider, right? We are majority, I think here, we are civil engineers, architects, construction professionals, but we need to understand this causing reaction, because this is the main motivation to try to reduce the emissions during the production of cement Portland. We have in terms of the carbon dioxide emissions, when you have the cement plant, we have these two main sources of categories: combustion, 4%, and calcination, right? So we have in different stages of the process, it's significant, the amount of carbon dioxide emissions, since we have the extraction and transportation, when you have the extraction of raw materials, right? But I will highlight this point here. But at the moment that you have a heating and the clinker production, this is one of the main problems related to carbon emissions at the moment that you have the production of clinker. Clinker, you can say, clinker is the pure cement Portland. And then you have all the stages in terms of the finishing products, transport, and utilization. So regarding the raw materials, we have limestone, right? And when you put the limestone into the oven and you increase the temperature, you have the carbon dioxide emission, right? This is one of the main components of cement Portland. So the indication nowadays, we can ask this question: how much carbon emission is released? Now we know we have this average 1 ton of cement release around 1 ton of carbon emission equivalent. But if you go through the literature, there is an average between 0.5, 0.6, but it doesn't matter. It's that everywhere the industry is trying to find alternatives to reduce the amount of carbon dioxide emission. And yeah, here you have the answer for your question, for very recent data available. And yeah, we can see the production, the cement production in China is almost the half if you compare with the half of with the rest of the world. So China's cement production shares equate to over half of the world cement production. So, what we need to consider as well is when you have the manufacturing, we have the cement manufacturing, the amount of carbon emission, right? This is recent data from 2019, but just to give you a broad idea, over the last 20 years, Vietnam, as you can see here, Vietnam is in the 3rd place. We're just thinking about China, India, USA, but you have other countries because it's also related to the economic growth in different countries, right? The cement production. So when you just combine these 3 main countries, we have almost 800 in terms of the gigatons, million metric tons emitted. So here is just to clarify the context in terms of different countries, in terms of production, and it's how we can at least demonstrate how this topic is relevant in our career, in our industry, in our workplace. And here, yeah, again, it's just to highlight, just to give you an idea in terms of the timeline and regarding the carbon emission, pretty much the process, the manufacturing process, it appears, it shows here its contribution. We have some minor contribution regarding the transportation, but also significant contribution depends on the fuel at the process of, at the manufacturing process of cement. And you have these statistics and these data available globally, 5% of greenhouse gas emissions for making cement, right? And yeah, and there are some expectations to grow. So let's try to find alternatives to reduce this problem. This is our main goal today. So let's move to the next one. If there is some, so as mentioned before, and when you produce the process, during the process, the production of clinker is one of the main, the main stage when you have the significant amount of carbon emission. So since the carbon dioxide for the production it counts approximately 85% of the total carbon emission of concrete, right? We have one of the main challenges for us is how we can reduce the amount of clinker when you are, the amount of cement Portland when you are producing concrete. So there are several alternatives that we can implement. And let's have a look at this. There are opportunities to reduce the emissions from clinker, alternatives decarbonated materials. It's one of the one of the alternatives we can identify if you go through the recent research into this area. Waste materials and byproducts from other industry to replace some of the limestone, because this is one of the raw materials, and when you have this into the oven and you heat, when you increase the temperature, this is exactly the moment that you have the significant carbon dioxide emission. So we have now new types of cement clinkers developed around the globe, and their expectations for example, the bureau in Europe, the cement bureau, using these alternatives here, implementing 6%, using 6% alternative fuels, using biomass containing 30% of biomass can be one of the potential alternatives to mitigate carbon dioxide emission. So these are some the co-processing. During the manufacturing process, we can use, it's possible, the cement industry is trying to use waste from demolition waste, colored slag, waste, lime as a co-processing and use the biomass. So these are simple, not super simple, but there are viable alternatives the cement industry is looking for to mitigate the emission, okay, to reduce the emission. And examples, you can have these different types of cements, like ferro-aluminate clinker, belite aluminate, ferrite clinker. All these are new alternatives that the industry is looking for and try to implement. In my opinion, honestly, in my opinion, cementitious materials, first of all, let's understand cementitious materials as we know why the main problem related to the carbon dioxide emission is the cement production, cement Portland. We have the raw material, we have limestone, we put this in the oven, we have the significant carbon emission. This is something that we know from the previous slides. And now we have alternatives. We can replace cement Portland, the pure cement Portland. We can, depends on your country, depends on the supply as well. The most common ones, for example, here in Australia, fly ash. In other countries, I actually believe in America and USA, different countries, because fly ash is a byproduct of burning coal, right, in the thermal power stations. So fly ash, we call it all these fly ash, silica fume, the slag, rice husk ash, sugarcane bagasse ash, all these materials are considered pozzolanic materials. And it can present some cementitious properties. Right? That's why we can replace cement Portland by these different types of materials. With the ratio can be around 30% of replacement, 70% of replacement. So this is some results we have from the literature. The main target is to identify, regarding this type of materials, the ones showing a significant content of silicon dioxide, because this is the fundamentals to obtain the pozzolanic activity. So we call it also supplementary cementitious materials. We have blended cement in the market available. Nowadays we have this available. It's a very important point that we can, straight away, we can start selecting materials according to its composition. That's why, first of all, we need to understand the material's characteristics, the material's property, because at the moment that we need to select materials, we can balance, right, in terms of the mechanical property we are expecting, but also in terms of the environmental impacts related to this material we are selecting. So fly ash, for example, if there is no problem in terms of supply of fly ash. That's why the cement industry is producing blended cement using fly ash into the replacement rate about 50%, 60%, or 70%, because it can influence the concrete properties, can improve concrete properties such as workability, pumpability, final compressive strength, and also durability of concrete. So this is nothing new, I can tell you. This is not the novelty for today, because these type of studies have been published in the literature for a long time. And exactly at this point, I started my interest into this area, and pretty much I've worked with ceramic waste. Yeah, sometimes you have some demolition waste and a lot of ceramic waste, and you have some treatment. You can transform this waste in this type of waste in something useful for the industry. This is something that researchers are doing around the globe. So this is an idea about cementitious materials. And till now, we discussed the emissions, right? Pretty much related to the manufacturing, the manufacturing process of cement Portland. Now we know this is one of aggregates. If you think about sand, if you think about coarse aggregates or different types of rocks, think about carbon emissions is not super relevant, because it's more about the transportation of these type of materials. It's not about the manufacturing, the production of sand, or the production of coarse aggregates. It's all about the production of cement Portland. So we talked about the emissions alternatives. We can replace part of cement Portland by, if you can use supplemented cementitious materials such as fly ash, such as silica fumes, such as sugarcane bagasse ash. It depends on your country. But on the other hand, as I mentioned here, concrete, it is something that the recent publications is more evident nowadays in today's area. On the other hand, concrete can absorb carbon dioxide, right? It's not new. The carbonation is the reaction of carbon dioxide available into the environment, and it will react with the calcium hydroxide into the cement paste, right? It's not new. But here I'm gonna pause and ask you another question. Just please have a look into this slide. Reflect on the decarbonation of concrete. We have decarbonation of reinforced concrete, and then you're gonna be able to let me know what you think about it. Carbonation reaction, it's a good alternative or not? Let's have a think about this, and then we can continue our discussion. But I wanted to reflect, because, yeah, concrete can store carbon dioxide, right? Because concrete naturally absorbs carbon dioxide during its lifetime. And you have this process. This process, we call it carbonation. And nowadays, regarding all these research under this topic, we are around this topic, we also call it recarbonation. So I want to think about this, because what's happening here? Carbonation is the reversible reaction. It's calcination, right? What we have? We have the carbon dioxide absorbed here, right? And we have the carbonation. So concrete will absorb, will store carbon dioxide. But over time, we need to be very careful with this alternative. It's something that we cannot avoid. It's inherent to concrete properties. It's all about concrete durability properties as well. But the literature is trying to balance this question, right? If it's good or bad to the concrete life service. Because, yeah, this is, Don, thank you so much. This is my main concern as well, because, you know, we have, in terms of carbonation, when you have the reinforced concrete, right? We need to be very careful in terms of the corrosion of concrete. And that's why we need to consider the cover, the minimum cover here is just a suggestion. So we need to pay attention to the pH of concrete. Otherwise, as you mentioned here, we can see, yeah, there are some pros and cons, as you can see. Concrete is a porous material, right, Thomas? I can understand your point as well. And yeah, so this is the big questions, Manesh. If the concrete can decarbonize the environment, that is something that you'll be discussing today, right? I think it's not right or wrong. It's not yes or no till now, because there are a lot of research involved into this going on into this around this topic. So yeah, but now I raised the problem. We have a solution, but we need to think about this, one of these solutions, right? We don't want our life service of lifetime of concrete with over time. We don't want the corrosion of the our reinforcement bars, our steel bars. So it's a lot of controversial topic, this one, but yeah. The literature just shows us that the carbon capture and utilization, CCU, can contribute to mitigate carbon dioxide, can store around 0.1 to 1.4 gigatons of carbon dioxide. This is a very recent publication. Because, in the long term, if you think about long term, I can tell you, we can consider the absorption of carbon dioxide and to form some stable carbonate beyond the lifetime of the infrastructure, more than 6 years. So points that to consider, we know that the carbonation process is a slow process. The time is an important aspect to have in mind, to consider as well. The transport of carbon dioxide molecules is also an important factor, just as Thomas mentioned, because it can also densify the cement matrix, so definitely can contribute to reduce concrete porosity, concrete permeability, and at the end of the day, improve concrete compressive strength. But as I mentioned before, it's not like simple like this. We need to balance all the pros and cons, right? And the water is required for the carbonation to take place. So based on these points, there are also other discussions that I will be touching base today. So literature also inform us, researchers, the authors are sharing this type of information. The built environment, we know that recarbonation occurs naturally in our concrete infrastructure. And there are some reputable source of information sharing with us that 23% of carbon dioxide emission can be captured annually. It can equate 80% of saving total carbon dioxide emissions from the cement manufacturer. So it's a natural process. We have the carbon dioxide, we have the concrete, and that's why recarbonation, one of the points that we can highlight regarding the recarbonation, let's say if you have a building, a concrete building or a stadium, and you have the demolition of this building. So this is one of the potential alternatives when you can reuse the recycled concrete aggregates. So when you increase the surface area, the aggregate, the recycled concrete aggregate, can also absorb carbon dioxide easily, and then you can reuse to produce a new concrete. right? Just to combine with the cement Portland, water, and sand. So here we have, just to touch base, just to the main idea today is to share with you, if you are not familiar with the topic, what we have nowadays in terms of the trends in research around this topic. So when you talk about the carbon capture and utilization, CCU, what's the alternatives under this topic? If you go through, it's just a summary what in relation what we have regarding the literature. We have the carbonation of recycled concrete aggregates. We have CO2, carbon dioxide in alternative carbon magnesium based binders. We have the mineralization in industrial waste. We have alternatives using carbon dioxide into the concrete mixing water. And in this case, in concrete mixing, we have some good results available in the literature showing that carbon dioxide injected into the fresh concrete during the batch and mixing can also improve the final mechanical properties. And we also have into this stage, because you know, the concrete, we have a composite material, we have the ingredients, we have the mixing of these ingredients, and then we have the curing process. And it's something that when you think about prefabrication, this can be a viable alternative when you have the carbon dioxide utilized as a curing agent to accelerate the precast concrete fabrication. So these, what I'm trying here is just to summarize what we have available into the more recent trends to the literature around this topic. When you have the carbonation of cementitious materials, this is the researchers are saying that it's a very attractive option to reduce the environment costs of concrete production, because you have the carbonation. First of all, carbonation, when you have the carbonation of cementitious materials like fly ash or slag, it can strengthen the carbonation can strengthen the cementitious materials and also can reduce the use of the pure clinker, the pure Portland cement. And also, yeah, the second alternative is just to absorb and sequester carbon dioxide. So let's have a look into some of these alternatives into details. And I will start with when you can use carbon dioxide, the literature called it carbon condition. Carbon condition, you have the recycled aggregate. Recycled aggregate, as you know, we have construction and demolition waste. More and more, we are trying to reduce the amount of construction demolition waste in landfill. So one of the potential alternatives everywhere nowadays in different countries is to reuse construction demolition waste in the form of recycled aggregate. But we know that it's not super simple to compare the characteristics of recycled aggregate when you compare recycled aggregate and the natural aggregates. There are some influences into the final mechanical properties of concrete. And now it's a common sense when some treatments can be done to improve the characteristics of recycled aggregate. And one of the potential alternatives is carbon condition. So this is retrieved from the literature as well, just to show you that you have here the recycled aggregate and you have a sealed chamber and you can inject carbon dioxide. And this carbon dioxide, the carbon condition, will improve the recycled aggregate characteristics. So, and then you can use the aggregate. Nowadays, it's quite easy to observe into the literature into the recent publications that you can use recycled aggregate, not as in both situations, structural concrete and also non-structural concrete. We know that the main application is roads and pavement, but we can also, if you improve the quality of recycled aggregate, definitely you can use these as in structural concrete as well. So this strengthens the attaches of the cement of recycled aggregate and gonna improve its characteristics. And if you are improving the characteristic of aggregate, just bear in mind, aggregate, if you look into the entire composition of concrete, we have around 80% of aggregate, right? 75, 80% is all about the aggregate. So this is a potential alternative you have here. And we can also have alternatives in the magnesium oxide-based binders. When you have the clinkering temperatures, this is one of when you have the reactive magnesium oxide binder. This can present some advantage when you compare with the common Portland cement, because it can also absorb carbon dioxide while gaining strength. But I need to highlight this point. Life cycle assessment, all these alternatives, we need to be very careful, right? That's why life cycle assessment is one of the methods that we have that we can balance the pros and cons when you have such alternative. If I'm going to use some recycled aggregate, if I'm going to use a different type of binder. So how we can do this? We can definitely use this methodology if you are familiar with this one. If not, it's just to understand every time as engineers, we need to balance, right? The pros and cons and the benefits and the costs, and one of the methods we can use to evaluate environmental impact, because we are talking about the advantages of these alternatives. We are considering all these alternatives to mitigate carbon dioxide emission, but we need numbers, and how we can do this via life cycle assessment. So some ideas when you have this reactive binder, and the other one I will be sharing with you today is during the curing process. The curing process, when you can use the carbon curing carbonate, when we have, for example, here is we have the concrete blocks, but also can be some concrete, and that's why it's very useful when you think about prefabrication, because you can use this technique, then this can accelerate the curing period. Because as you know, in situ concrete curing, sometimes we need to wait 7 days, 14 days. That's why prefabrication can be a potential alternative as well, because if you just make it more efficient when you have the accelerated curing, definitely we can improve the concrete quality. And it is all we need. We are working with a composite material, and what we want concrete to be a durable material over the life service in more than 20, 30, 15 years. We can think about Pantheon. This is a real concrete, and it's a real example, it's a concrete example of durability. And let's go back to here. So carbon dioxide can be used as a curing agent, right? And is one of the alternatives. And we know that this can be, if you think about the advantages, and the advantages can be a potential solution, because you can use this in prefabrication. And regarding this current challenge we are facing, the urgency to mitigate greenhouse gas emissions, that's why the researchers around the globe are trying to collect more and more data, more and more information about these alternatives. So one of the main advantages about the rapid strength gain, when you have the carbon dioxide, when the carbon curing, even when you're working with conventional concrete using Portland cement. So some alternatives here. And mineral sequestration. This is pretty much the continuation of the topic, because here we have the industrial waste materials, and the waste materials, the mineral sequestration, we have, this is something that more recent. For example, we have, as mentioned before, what type of waste materials, byproducts, as I'm just reinforcing and highlighting the most common ones, such as fly ash, slag, and recycled concrete aggregates, because these materials can be treated, and when you have the mineral CO2, when you have the injection of carbon dioxide. And decarbonation, so from the literature, there are alternatives of this type of sequestration when you have decarbonation approach, can be aqueous or gas solid. So these are the factors that you need to be considered when you are targeting this type of treatment, when you're using fly ash or the slag. This type of carbonation, the carbonation approach, and also decarbonation efficient. Okay, so I don't want to go through the details here, but the main idea is to highlight and to call your attention that do have some different studies on accelerated carbonation treatment of recycled concrete, fly ash, slag. And this is the type of, can you imagine, this is type of treatment that you can maximize the carbon dioxide uptake and the capacity of these materials. So, yeah, and the researchers are comparing the most efficient ones, right? This is something. And other factors that we need to consider when working with the sequestration carbon dioxide is regarding the chemical compositions, the particle sizes. So here I just want to show you that there are so many details that you need to consider. At the end of the day, it's all about analysis in terms of not only about the environmental impact, but in terms of the benefits regarding the concrete properties. It's a huge responsibility, right? The structural engineers. And yeah, and here is to illustrate, I think I really like this diagram from this source. It is very, very new reference, and I'm sharing all the reference with you at the end. Because we have here, this is our target, carbon dioxide. In terms of, it's very simple to understand because you have two alternatives. We have the carbon dioxide sequestration, when you have the fly ash, when you have recycled aggregate. We have the I can call it a pre-treatment. And this treatment, the main target, reduce carbon footprint in the concrete industry. It has been investigated extensively everywhere around the globe. So carbonation treatment, the main idea is to convert the carbon dioxide into carbonate minerals. So we have this part. And okay, we have the materials. Then we can also, during the mixture of concrete, we can also inject carbon dioxide, right? So we can incorporate these carbonated materials, and you can mix the concrete, and the final concrete we can use in buildings, bridges, and the main idea is to balance the cost and energy efficiency. This is all about a life cycle assessment to gain this feeling and to get the numbers, because at the end we want to see numbers, right? And the other alternative, let's say we are working with the materials treated here, right? We mixed concrete, and also we can also combine it with the carbonation coating if you're working with a prefabrication, right? And then it's another alternative just to absorb more and more, store more and more carbon dioxide. And the benefits: increase the resource in terms of efficiency and reduce carbon footprint. So here we have the summary, because what we want for a specific material that may exist and can have the carbon dioxide uptake threshold. So we need to balance. There is a limit to uptake carbon dioxide in terms of the materials treatment, right? Otherwise, we don't want it to be deleterious in the future. We don't want these to compromise the mechanical properties of concrete. Similarly, as we discussed before regarding concrete carbonation, we know that concrete can absorb carbon, definitely can contribute to the carbon, to mitigate carbon dioxide into the air. But at the same time, we need to consider if it can compromise the durability of the material. So all these challenges are nowadays in our hands. So yeah, but here I'm just going to share some interesting applications. For example, we may discuss the carbon condition of recycled aggregates. There are some different, what we have in terms of the literature we have. For here we have our reference concrete without treatment, and then we can see the compressive strength of the other concretes treated. When the recycled aggregate is treated, he got the carbon condition. We have the injection of carbon dioxide. So, and here is just to illustrate, we have, here is just a combination. We can replace natural aggregate by recycled aggregate, and also these comparisons also includes the carbon condition as well. So, but here is just to demonstrate that you have the concrete, our reference concrete, and you have the concrete when you incorporate recycled aggregate, and sometimes can, and in this case, showing higher compressive strength. So it's just to show you that it's all viable. So it's also a question of knowledge, right? That's why we really need to be totally aware about what researchers are doing around the globe. And this one is an interesting, when you are working with supplemented cementitious materials, is this one is an example of a carbon dioxide uptake of fly ash. And you can see here we have a very simple example when you have the mortar with the untreated slag, and here the carbonated slag. It's the significant improvement, right, when you compare. So everything is to show you that it's possible, right? That's why the industry is targeting and is supporting, I can tell you, the cement industry is having a lot of collaboration with different universities around the globe just to try to find positive solutions. So the mineral sequestration at this is the target and this is the challenge as well, the commercial scale, right? And because, you know, they have the environmental impact, to have the accelerated carbonation treatment, but we need to also consider the energy consumption, right? So that's why we need to become more and more familiar with the life cycle assessment, how we can understand if these alternatives we have, because there's always two sides, right? We have the carbon emissions higher than the carbon dioxide sequestration, or we have the higher carbon dioxide sequestration rather than carbon emission. That's why it's a balance. This is the beauty around when you are working with concrete. We have this material is a fantastic materials that you can also, we have the problems of this material, but the same material can provide you with so beautiful solutions. So yeah, this is our main challenge as researchers and engineers. And here is more to give you something just to summarize the main content we covered before. The carbon dioxide to produce ready-mixed concrete, injection of carbon dioxide during this stage, the batching and mixing, and also the carbon dioxide can allow 5% to 80% reduction into binder loading without compromising strength. There are numbers retrieved from the literature, reputable source of information, believe me. And the carbon dioxide can be delivered into the fresh concrete, right? So different stages of concrete. Since we started selecting materials to produce concrete during the mixing process and during the curing process until the end of life. So this is, I like to show you numbers as well because we want these, we like these. This is a very interesting result from McDonald and Monkman when they could find, this is high strength concrete in my humble opinion, right? Around the 7 megapascals, 8 megapascal, they could find, they could produce with the, and they could reduce the amount of cement, Portland cement, around 6%, and they could just highlight it. It's just good to know how we can estimate the proper dosage of carbon dioxide. And here it is just to illustrate 0.518% by weight of cement. And here it's just to compare the reference, the control mix, and the carbon dioxide mix. Slightly improvement here, 7 days, but significant improvement at 28 days. So again, it's just to share with you that it's possible, right? We can trust. And yeah, the current improvements, as mentioned before, everywhere around the globe, the cement associations, we have this target, right? The progress to date in terms of the production, how it's possible to reduce carbon dioxide, you can see it's not that bad, right? Everywhere they are blaming the concrete and cementitious industry regarding the carbon dioxide emission, but they are doing a great job to reduce the fossil fuel, right? So because when you substitute by biomass or we have the co-processing, the alternative, what type of alternative? You have the municipal and industrial waste. This can be used as fuel, right? And reducing carbon dioxide, we can reduce the dependence on fossil fuel. We're gonna not get rid of it. It's not possible. We need to be realistic. But material recycling and alternatives to landfill. This is our dream, right? And improve energy efficiency during the manufacturing process. So structural engineers, yeah, we need to consider, since the design aspects, it's possible to reduce carbon dioxide. There are some studies in this, just about the building design. You know, if you reduce the amount of concrete, definitely you're going to reduce the embodied carbon into this building design. Older buildings, we can try to reuse the concrete structure of a building rather than demolishing it entirely. Honestly, quickly, I know that you're almost at the end. I am neighbor here of the Waka, the cricket stadiums here in Perth, and they are huge demolition going on there. And I'm asking why and why, because they want to rebuild in a new complex and a new complex leisure center. But it's very sad when you see this amount of concrete is a waste at the moment. So that's why we need to target. That's why we need to work in a multidisciplinary team. Please, architects, engineers, construction professionals, work together. We need to design for the construction. And yeah, it's assemble and disassemble. This is something, disassembly, right? At the end of life. So designing. Building information modeling, all these new technologies, we need to modernize our industry. We are very traditional, right? But the time is changing, and yeah, some summary from our session today. We have alternatives, favorable alternatives to make carbonate and require less energy inputs. And we also have the carbon capture utilization technologies using the building materials, mineralization of carbonate, aggregates, all the technologies we discussed today. And there are some real examples around the globe. Here is just, I just highlighted this one. So aggregates used in construction, recycled aggregates, and we can use the carbon condition and improve the final results. And 56% is emissions raw materials, right? As much as you can reduce the amount of raw materials, natural materials, we can avoid the depletion of natural resource. And yeah, every single step can be a contribution to reduce carbon dioxide emission and reabsorbed carbonation of concrete. By carbonation of concrete, we are still in doubt if it's good or bad, but I truly believe it's only a question of balance. And yeah, the end of, we need to, partly during the use phase, the concrete products, and the end of life and secondary use stage. So here I'm sharing with you the reference. I've tried to consolidate and to summarize the content from different reputable sources, information. That's why I'm sharing here with you. And yes, I'm really glad that you all came, and I think we can contribute in our workplace with these new, some not very, very new ideas, but current ideas.
Thank you, Dr. Anna, for addressing some of the key considerations around using concrete as a construction material, and also discussing some of the alternatives. And thank you, everyone, for participating. There will definitely be a time for a short Q&A session soon. But before we proceed, I just want to mention the upcoming webinars and the courses we have scheduled. So our next technical topical webinar will be on the 16th of June, which is next week. That's on the topic of introducing augmented virtuality to Industry 4.0 and beyond. This webinar will be presented by Dr. AK, our EIT lecturer and course coordinator for Industrial Automation Engineering. We also have another tech topical webinar the following week on June 23rd. That's on the importance of considering the 3 sustainable pillars in construction. This one will be presented by also another one of our experienced EIT lecturer, Caroline. Yeah, all of these technical webinars will be held weekly every Wednesday at the same time as this webinar, 3 p.m. Australian Western Standard Time, and it will be delivered online. If you are interested to attend, you can register on our events page. It's also provided there on the slides, and all the details will be on the page. If you click on it, next slide, Anna. Just to introduce some of our upcoming courses, we have a professional certificate and of competency as well as advanced diploma and diploma. These courses run across throughout the year, and we have multiple course intakes for them. We have our professional certificate of competency. These are our 3-month professional development short courses. Yes, as mentioned, they run throughout the year, multiple course intakes, and we have a number of electrical professional certificates actually starting this June. There's also our undergraduate certificates and bachelor qualifications starting this July, and also the graduate certificates and masters starting January 2023 next year. So most of the units in the undergrad certs and the graduate certificate are drawn from the bachelor's and master's degrees respectively. So if you have completed those qualifications, it might provide a credit pathway into a bachelor's or master's if you meet the eligibility criteria and you choose to pursue a higher qualification with us. And these courses are only 6 months for the graduate certificates and undergraduate certificate qualifications. We also have our on-campus intake starting soon in August. We have courses available across bachelor's, master's, and doctorate for on-campus, and a number of bachelor's and master's qualifications are actually accredited by Engineers Australia and also recognized by international courts, specifically Sydney and Washington courts. Yeah, and lastly, as a quick reminder, we don't forget to scan the QR code. I know there are a lot of messages in the chat box. Anna, could you go to the next slide? In the chat
Yes.
box asking about the certificate of attendance. Yes, you will. We will be sending these slides after the webinar session has ended, and you will be able to scan the QR code. Or if you're not able to, there's the QR link that you can also access. There you can fill up your survey, and from there we will be able to send you the certificate of attendance, and that is between. We need to give us a couple of days, and it has to be done within the specified time frame. If not, we are unfortunately unable to send you the certificate. So yes, thank you everyone. We can have start our short Q&A session now. So please feel free to ask Dr. Anna any questions. I've also seen some in the chat box. We will, don't worry, we will address that as well.
So thank you all. Thank you everyone for coming. Please keep in touch if you have any questions. If it's not now, later on, you can contact us anytime. Okay?
Yep, I'm seeing one. Anna, someone.
Yes, Jack. To reuse the concrete materials, what is the guarantee period that should be given to the? In fact, the regulations nowadays, if you go through, for example, if you're going to work with a structural concrete using recycled aggregates, definitely you need to follow, depends on your country, the standards you have available, but in terms of the guarantee, it should be pretty much the same as when you are working with a conventional concrete. But yeah, depends on your country, depends on the policies available in your country. But this is the main challenge when you are moving from the traditional, conventional concrete to the recycled concrete when you use recycled aggregates or recycled materials. This, I understand, this is one of the main questions. That's why all the standards, and if you are working according to the standards available in your country, you're going to have the guarantee.
I think we have another question, Anna. How about the reusability of the reused concrete?
The reusability of the used concrete. Okay. Let's manage, if I understand, the main, when you have the demolition of a concrete building or a concrete structure, and you can transform this concrete into the recycled concrete aggregate, you can reuse these as to replace a part of the natural aggregate. So, and let's say you are working, if I understand, okay, now you have a new building, you have this done, constructed using recycled concrete, and you're going to demolish it again. You can reuse again, you know. And that's why all these studies around the treatment, how we can improve recycled aggregate, the characteristics of these recycled materials.
Yep, we'll just have a couple more questions.
Yeah, Jill, I think about the sugarcane bagasse ash. This one is, you know, depends on, as mentioned before, depends on your country, because what's the main constraint from my point of view is in terms of the supply, right? Because you can, fly ash you have abundant everywhere, right? But sugarcane bagasse, to make it in the commercial scale, it's quite difficult at the moment, but let's say in a specific region, you can replace, some studies available in the literature showing that you can replace 20%, 30% of the cement Portland by sugarcane bagasse ash. It's viable technically. And you can obtain the same level of compressive strength, because it's all about the content of silica dioxide, amorphous silica dioxide, because it can present some cementitious properties, the sugarcane bagasse has. It's a very interesting material that you can use. Similarly, you have the rice husk ash.
Thanks, Anna. Maybe just one last question. If anyone has any more questions, just put it in the chat box and we will have to end off the session soon.
Okay, I can see Darshak, how
Yeah, you
effective
can.
can recycled plastics tied when using the concrete instead of raw. Yeah, depends on, we have different alternatives. For example, we can use some plastic waste to replace, let's say, the fraction of fine aggregate or part of coarse aggregate by plastic, depends on the condition. There are different studies using the waste of plastic, how we can incorporate it in concrete. And the tires, the waste of tires can be also used into these fractions. It depends on the size. You can replace the fraction of fine aggregate, or you can use as fiber, or you can use in a cement asphalt as well. There are different possibilities, not only one possibility.
Right. Thank you, everyone. Thank you, Dr. Anna. So if you guys do have any other questions, please visit our EIT website or email us. And I know as you're getting a lot of questions about the certificate, as long as you have attended this live session, we will send you a copy of this presentation slides, and it will also include the QR codes, and that's where you can request for a certificate of attendance. So yes, thank you everyone for attending this session, and see you guys in the next webinar. Thank you everyone.
Thank you everyone. Take care.